Okay, hi everyone. So today, Phương will present a paper titled Introducing the Expohedron for Efficient Pareto-optimal Fairness Utility Amortization in Repeated Rankings. This paper is published in Wisdom, right? If I'm not wrong.
No, I think it's not wisdom. Let me check that. Um,
Six IR, right? Or Wisdom. It's
yeah.
Wisdom 2022.
Okay.
Okay, so yeah, over to you, Phương.
Okay. Today I'm gonna talk about a new way to produce the Pareto optimal in the repeat ranking. So, uh, yes. Today to for the for everyone who doesn't understand or maybe really familiar with this theme, I'm gonna talk about first about the recommended system, and after that is the Pareto front and the need of Pareto front in the recommended system. After that, we are going to the real problem in this paper, what the scientists have done and what the author have proposed a new method for the problem. The experimental result of the problem and some limitation and future work. Um, so the first of all, what is the recommended system? For the one who don't familiar with this, I think that most of us have used some kind of recommended system like the Netflix. You can see that maybe the topic for Joshua or maybe the because you watch macro, so it's some kind like they see what have you done and they might the platform I think that you're gonna know or maybe like what they recommend. So the engine, the secret behind the list is the recommended system. Another example is maybe Shopee. You when you add some product into your cart, or maybe when payment check, you will see that when you scroll down, you will see something like you might also like, but how do they really know that you like it or not? So that is another example of recommender system. And the final is maybe the TikTok. You will see that you can see a lot of things that TikTok will just you will only scroll your screen and see what the platform recommended for you. You really don't have to like choose or maybe sign anything. They just see your action, uh, calculate the time you're spending on the screen and decide do you like it or what you will like next. So that's why you can see that a lot of people spend a lot of time on the TikTok. Like that's why they usually say that it kind of like manipulate your times. So that's an example of recommended system in the real world. To be formulated into the problem, we can see that given a query, maybe when user login, a search add item to the cart, or maybe the platform try to create a promotion email for you, and maybe some context like what is your user ID, what is your search history, your like history, or maybe some keyword you have searched. So what should we recommend for you so you will continuously buy or maybe staying with our platform? So for the last system, like they had a lot of items like Shopee, Lazada, or some e-commerce platform like that. We have thousands, maybe millions of items. So first of all, they need to limit the number of items they will recommend for you. That's the first step. And after that, what the order of this number should be displayed? Because you when you search in Google, obviously you just consider about one or maybe three first recommend maybe first result in the searching screen, and if you scroll to the down downside, you will see that there will be maybe a lot hundred of thousands of searching paper after that, but you rarely click more than 3 pages. So basically, the order of item will uh, like show that you only care about some first item in the list. So the order of this item is very important for the item to be shown in you. Uh, uh, Another thing you might want to know that we have three kind of recommender system. The first is collaborative filtering. Um, this kind of recommender system will like based on your interaction activity between you and the product, the item on the platform. So they like will compare you with other people like um, and maybe item with other item too. So they will have the main idea that you might like some item or maybe some product that people like you or maybe similar to you like. It like create a group of having similar behavior, activity, something, and try to recommend the same item for all of them. The second type of recommender system is content based. You will see that when you like searching a movie or maybe you type a keyword, a name of director or actor, and they will show that the list of films that have the keyword, have that genre, maybe be directed by your favorite director. So that is kind of content based. And for the mode of efficient recommender system now, mostly they are most of them are hybrid recommender system. That's like when you try to recommend something for you, they will see your history. They try to predict who you are, what is your hobby, your favorite um, film, movie, something like that. And based on what you have recently shared, the hottest trends, and they will recommend something for you. Um, so that the basic three kind of recommender system. And now to the Pareto front and why we need any recommender system. The reason we need something like the Pareto front in recommender system, we will need to answer some question. First, do the user is the only concern of the platform? No, because the platform make the profit mainly from the provider. So to keep the platform like long-term lasting, they have to satisfy the provider to provide a more diverse, a more content for the user to stay with them. The second question is, uh, do the provider have competition? Yes, because as we can see that uh, uh, as I said previous, that the position of the item in the recommended list is very important. And because you only see about maybe 3 or 5 first position in the recommend list, uh, when a provider maybe of 10,000, maybe 100, a provider, they will like compete for each other to earn a spot, a position in your recommended list. So they have to compete with each other. So to keep the provider staying with the platform, some fairness may be guaranteed because when the provider like see that the item is not being exposed in the list, that so the user will know nothing about the provider at all. So they will just simply leave the platform and find a new place for you for them to like showing their good and uh, attract more customer. And finally, you will see that the um, provider fairness and the user utility will have some conflict because as a user, when you search something, when you see a recommend, you always hope or expect that the list will like the will be understand you the most, the list will fit your hobby the most. But some provider just simply want that every customer know about their range, their item. They can be the famous or popular item on the platform. So obviously there is a conflict between the two objectives. So when you have to decide which order or maybe which recommender list should be displayed for the user, you have to consider it about the trade-off between the two objectives. First is the user, the life of the platform, and secondly, the provider fairness. We keep your platform long last. So, um, mm, one of the most efficient way to decide which recommend list to choose as you could draw a whole line, like draw the whole boundary to see that if I select this solution, how fairness or maybe what is the utility of user gain, and how much could I extend the user utility for the provider fairness. So the boundary like that, the trade-off curve you see in this is what called a Pareto front. It will show the trade-off between the level of usability and the provider fairness or maybe unfairness. And the set of the solution to create this kind of objective, it called is called a Pareto set. You can see the definition in a lot of uh, problem relate the multi-objective problem. Um, so that's the background, the basic information you need to know before we start the problem. So back to our main problem here. Give a query or maybe a user action like we said before, a login, an add to cart, or maybe create a promotion item email. We will have like a black box search engine to give the platform the relevant vector score of the item. This black box search engine could be the BPR or like GPM or maybe neuron. What there's a lot of choice for you, but all we need to know that some previous engine will give us some relevant score of this item to the query. This score shows that how much the item relate to to the query and the user. So we will know that if we chose this item for the query or maybe for the user, how like what how many utility from the user could we gain from that item. So the second thing we had to decide the order of the item in the recommended list. So which order should we choose to to narrow the problem here? Where we have some assumption that first, each item will belong to only one provider, and one provider will provide one item only. It's mean we will consider it that um, each item now will be one provider, and we will try to guarantee the item fairness instead of provider fairness. So the second assumption is, as we said before, that the each position in the recommended list in the display screen will have a different exposure score, and since we know that they will like degree uh, when the ranking go up, the exposure score or maybe the attention score from the user to the item will like degree. So in here we will choose exposure score for the ranking K will be the log function. Assume that the rank start from 1 to the end, with n this number of items we want to recommend in the recommended list. And finally, the final assume that the relevant score which the black box engine give us will be the true score of the item. So that is our assumption. So how do we define which order of this item? The first one, very basic, a simple one. You just try all the possible solution, which we call a brute force. Like we try every solution and calculate the objectives, the utility we gain from that, and try to compare and draw some align. So there will be, because this order, there will be the other permutation of recommended list. So the complexity may be uh, what and like to what do we call it?
It's
Uh,
factorial.
fact
Factorial.
yes, factorial. There will be n factorial with the with n is the number of items. So it's not really realistic because well, for usually when they recommend something, you will like about at least maybe 10 or maybe more. When in some large e-commerce platform, they will be 100. So the factorial of n will be very large, and none of this computer can do it for like fast enough to create a list in real time. So we have to choose another way, a different way. Um, for most of the research now, they use a ranking probability metric with the name of Birkhoff polytope. So this metric will have the meaning like at the cell EG, they will represent that item E should be recommended at the ranking K with what probability. This is an example of a recommended list with 3 items, and we have to try to order these 3. And after we have this prop probability metric, we could like sampling or maybe choose some kind of sampling strategy to create a recommended list from this. And for the long term, we will have some fairness as well as the optimal user utility. So to formulate the problem, we will have this like call the Markov prototype P is our variable we need to optimize. Rho is the relevant vector score, and epsilon star is the item fairness target of exposure we try to achieve. So for the different definition of item fair target, we will like have a different E star. And in here we will have 2 objectives. First is to maximize user utility is P times row and maybe time the ranking position in our recommender list. Like we always wants to like to have a most relevant item of our need, our query to the top search. So we might need a gamma or maybe an exposure ranking in here too. And the second objective is to minimize the item unfairness, which is the exposure score is L2 norms of exposure card exposure score to the item fair target exposure. So when, as you can see, that this will be a sim with the constraint that the sum according to row or column of the matrix here will be equal to 1. That the total probability of item to be which in position will be 1. So this will be a
Okay.
symbol.
Can you explain more like what is pi in this problem?
Yes. The pi in this problem will be our Protopia, our matrix of proper probability of item here.
Mhm.
So this is just an example, a sample of a prototype here, and a sample with 3 items. You will see that the sum of first row is 1, and the sum of first column is 1, 2.
So
We
it is a by stochastic matrix where
yes,
each row is sum to 1 and then each column is sum up to 1.
yeah.
Basically, each entry is basically showing the probability that the item will be in that position, right?
Yes. Yeah.
Okay. And there will be totally how many? What is the size of this Birkhoff?
The size of this Pareto is uh n times n.
N times n.
Yes.
It could be
Square
n
n square.
n square.
Yes, n square.
Okay, so the problem here is that you need to determine the value of the entries of this matrix so that well, when you multiply with row, it has a maximum value, and at the same time,
Yes.
uh, the L2 norm square will be minimized.
Yes, and maybe since we have a uh, different exposure in the ranking, and we assume that user want like the most relevant item to be the top of the list, this might be a time with some like maybe gamma, with the gamma is exposure ranking score like this.
So gamma is the exposure score.
Yes, exposure score when you are ranking k maybe gamma will maybe like one log log two of one of two for the item that will be recommended in the first list. One with
Mhm.
log two like three with the item in the second list. To the one divided by log two of n at one with the item in the last list. So this will like degree the first item. The item at the first position will receive the most of the exposure, the attention of user, and this attention will decrease by with the ranking.
Okay. If it is exposure vector, then it should only appear in the second function, right?
Yes, in second function, but when if you assume that user also want that the most relevant item to the query should be in the top list of the recommended list, maybe on in the searching, so they don't have to scroll down to find something similar to find the correct answer for them, because we assume that the relevant is the true. Here we assume that the relevant score vector is the true score. So when the user wants the highest relevant score to be the top, we will have like the times the gamma here to make sure that the higher relevant score will be in the top of the list.
Okay. Okay. So what we learn is all the xij, right?
We still learn pi because yes, we still learn xij. Yes, sorry, this will be pi. Sorry, it's my bad. Yes, this will be pi or maybe x.
Okay. And rho is given. Rho is a relevance.
Yes, row relevant score we given by the search engine here because we already given it. A Blackboard give the platform some relevant score vector engine. It's like the baseline recommended system try to predict what item be relevant to the query of the user, and we only care about the second phase when we have the item to recommend what order we should we display to the user. This is only the second step of the recommended system. Yeah, the first step is to decide what item should to be recommended, and the second step, this is what we do here.
Okay.
We decide the order of the items to be displayed. So,
Okay.
like we are
Then then
doing the
then
second
the
step.
then row will be depend on pi, right? I mean
Uh,
the
no,
the,
no.
the order of the item will decide the order
Uh,
of the elements in the row vector.
yes. The order of row will be decided by pi, but like the row is already given.
Then I think in this case it should be written as row pi, means that row depends on pi, right?
Yes. No, no. Actually, what row is not really depend on pi because row like the relevant score. So the pi is which order should you choose from row. The row will not change. Only the pi that dependently change from the row. So I don't think I think here row is correct, not like row pi because row have nothing to do with the pi.
Okay, okay, okay. Got it.
Yes. And as you can see here, when we did, we can solve with the linear programming, and we can like combine this with, to scalarize that to generate the Pareto front. So in that case, we'll have complexity of about n n hat 5 is quite large when like n go up. So because this like a query by recommender system, well, the recommend should be give after the query about maybe less than 1 second. It's still a very large. So do we could we reduce that work? The answer is yes. So this is what the paper Expohedron do. They propose a new method to generate the exact Pareto front as they claim with less complexity. So the question began when they try to reduce the number of variable from n squared to only n. So with the distribution d of the pi, we will have the exposure score could be computed like this. The sum of the probability with the exposure of pi. The pi is the Kolokov matrix here. And if we have a distribution d of the pi, we will have the exposure score in the probability score like this. So this is unchanged, and we could use this in the user utility as well as the item unfairness here. The user utility in the distribution d of pi would be the sigma sum of the probability p with the utility of user when we have the distribution of pi, and we could like decompose it to the p to the row t times with its exposure score of item have distribution d. The same way will be uh, we can do the same to have the unfinished score with the distribution d of pi and the target of epsilon star here. The norm 2 will not change. So we will have two objectives like this. One is to maximize the in like transpose row with the epsilon d here, and the minimizer item unfinished of norm 2 of epsilon d minus epsilon star here. So
So
as
this
you can
is the
see,
thing that you talked about earlier about adding the exposure score, right?
yes, so we will change the definition from our variable from the prototype input to the only the exposure score of item. And if we could like have an exposure score of item, we could decompose it to the probability matrix again before we try to sampling from that.
Okay.
So it like we have a three step before. Here we will have a three step, like we will from the maxima here, we try to populate the rank probability matrix here, and then we try to sampling from it. So this is our variable. Uh, but with this proposal method, we could like from directly start from the exposure score. We try to optimize this, and then we like try to decompose to some kind of matrix of probability like this before we sampling.
Mhm.
So from the different start point. So that's the basic idea. But again, when we change our variable from square n to only n, we will see that our constraint will change a little bit, because in here we will like have a linear constraint, but since we times some probability matrix in here, the constraint will make uh get bigger, get bigger from only the linear here. So we will need a different way to define the constraint.
Mhm.
So to define the constraint here, they use a new, not really a new idea, like an adapted idea of the expohedron. This expohedron start from the definition of permutohedron. Permutohedron is a way for you to define um, define all the permutation in the geometry space. In here, we have an example of permutation with three items, and the order start from the permutation from 1 to 3, 1, 3, 2, 2, 3, 1, 3, 2, 1 here, 3, 1, 2, and 2, 1, 3. You will see that we have 6, which a fraction of uh, factorization of 3 is 6. We have a 6 vertex here. This will create a hexagon here. So you can see that in the permutahedron display, the um, they will create some kind of like convex hyperplane uh, with factorization of n vertices, and you can can like display it in the uh, um, n minus one dimension. Here we have three like a three item, but we can see this just a hexagon in 2 dimensions, but you can see it here.
The order of the vertices, are they important or it doesn't matter?
Um, I think it don't really matter, because when you try to create a convex from the point, they still be like one convex. It will not change. You can
The im
start from this point, but
the
when you
importance is that no matter where you put the vertices or where you label the vertices, as long as
uh,
the shape is the polytope.
you can imagine it that each vertices will be one point in the hyperspace, because in here you can see that in 3 dimension space I select a point with the coordinate 1, 2, 3,
Mm.
and I connect one point with connect the 1, 3 through.
Yeah,
Uh,
but my point is that so in the figure on the left, 1, 2, 3 will be next to 1, 3, 2, right? And it's
yes.
opposite 3 to 1. Is that important, or it doesn't matter where these permutation are on the polytope? Like the position of the permutation, right? 1, 2, 3, is it always has to be next to 1, 3, 2 and 2, 1, 3, or it doesn't
Yeah.
matter?
I think that it will basically that's always be there, because it's like when you decide some point in the
Yeah, I understand,
hyper
but
dimension.
the position of this permutation, are they important or you can put them anywhere? So I can put 1, 2, 3 next to 2, 3, 1. Is that okay?
Um, I don't think that you can able to do that because the when you try to like create a convex from the point, I don't think that you can put it in the middle of that. You try to create the convex outside, just like you cannot like design any like edge or faces you want. It has to be a convex.
Yeah, this one I'm not sure I understand yet. Like, so 1, 2, 3, and on the left is 2, 1, 3, right? And on the right is 1, 3, 2.
So what you mean that you can might not have an edge here or we have a direct edge like this, right?
Yeah, or I can just move 3 to 1 to the position of
No, no,
one,
no.
three, two.
You can move any position here because it's just like a fixing point in the hyper in the high dimension.
Okay, so that's my question, right? Is it important that you have to follow some order, or it doesn't matter? I can put this permutation anywhere.
I think if I understand correct, your idea so because it must be a convex, so the order that the
No,
edge
no, the
or
shape the
face.
shape is still there. The polytope is still there, but how do you label the vertices? Is it important to follow some order, or it doesn't matter? You can put all of them in any places that you want, as long as they are the vertices of the polytope.
I think that order is important because I decided it to has to be a point. So when the order of the vertices, like the order of the permutation is 1, 2, 3, it has to be that uh, the coordinator x equal 1,
Mhm.
y equal 2, and 3 equal 3. So it has to be a fixed point for each permutation. It cannot change.
So 1, 2, 3 here basically denote the coordinate in some sort of.
Yes, yeah, yeah, yes.
I see. Okay.
So we will have a fixed permutation in
Okay.
all dimension. No,
Okay.
no, in all
Okay.
dimension.
If you put it in a
Coordinator space.
coordinate system, then it's basically like the position in that coordinate. Okay, got it.
Yes, the same one will happen with maybe n is 4. You will see here we have a 3D dimension, but actually this coordinator will be like in the 4D dimension. But since we cannot draw a 4D in here, we should just like draw the 3D Permutabhedron here. So you can imagine it how they will be in here.
Okay.
So you will see that each of the faces will be a cut, like a linear constraint cut
Mm-hmm.
a space and create this like a vertex.
Mm-hmm.
So if you try to like um uh, so uh, for the Expohedron, instead of the each coordinator here will be permutation, we will use the definition of the DCG utilities. It's like when the item of when item 2 item 1 here have position of 2, it will have the exposure score like this. And if the item 2 have the position 1 in the recommended list, it will have the exposure score like this. And vice versa for the 3 item 3.
Mm-hmm.
It's just like we just change the name here. Like not 1, 2, 3, but one fractal logarit true of 3. But the definition have not changed. It's just like we change the value of the vertex.
Mm-hmm.
So you will see it now for each of exposure score you could like uh, represent it with a point inside an expohedron. This
Mm-hmm.
will be a kind of major line like this. This major line will be like a point, so it will mean that an epsilon will be a point inside the expohedron created by the vertex is the vertex will be a permutation of the gamma here. This is the gamma.
Okay.
This is the gamma. So as I said before, you will see that in the permutahedron, maybe it's expohedron with the n is 4, you will see that each phase here, a cutting phase here will be a linear constraint for the for the permutahedron. So it come from just from two constraint from two linear constraint here to a lot of linear constraint, because we will have a lot of cutting point, a cutting plane here. And if my calculation is correct, it's maybe about 2 power n minus 2 number of cutting point if you try to like represent this majorite in the linear way. So to handle the linear is a big problem in the diagram.
The decision space now is only n elements and variables, right?
Yes, only n variable, but the constraint is way much more complex than the original one.
Okay.
So it's very hard for you to use like some kind of linear program to solve it.
Mm-hmm.
So yes, they come up another way to generate the Pareto front, that they solve it directly in the geometry way. So as you can see here, we have this an expohedron of uh, three, the three item, and assume that V0 is our initiate point, is the E star here. So this is the point that we will gain the extreme fairness of our user. And you will see that because this objective is like norm 2, so the level of the objective is like a circle around the V2 V0 here, which is E star here. And because this is just a linear, so the level of the user utility will be the blue line here, the blue line here. And you will see that if we follow the row, the transpose row from the V0, we will achieve higher and higher user utility. But because when we follow the transpose row here, we will also receive the more and more unfairness from the central of E star. So as long as we follow the transpose row here, we will have like a Pareto set, a point that trade between the fairness and the utilities. Do
So
you still with me?
so V here is
V0 here,
basically epsilon, right?
yes, epsilon star is our starting point here, because
So
this is just a
epsilon
norm.
0 is V0, right? Epsilon 0 is V0. You
Yes,
start
epsilon
you start
star.
with epsilon 0 equal V0, right?
Yes, because this is the point that we will gain extreme values here. And because it's norm 2, so there will be a circle around the central here.
So again, what is V0? V0 is
E star.
a
The E star.
epsilon
Yes,
star.
epsilon star. Epsilon star. Sorry.
Okay, so at the epsilon star. So okay. And what is a green line? The green
The green
line.
line. The green line is our optimal Pareto set. Because if we follow the green line here,
Uh-huh.
the green line here will have like a projection of row transport row in the space, like in our space, in our hyperplane here. We will see that if we follow the transport row, we will like have a degree level of user utility here. We just follow because it's linear. We have this thing in linear.
So the row
So
is a blue arrow, right? That is a blue arrow.
yes, this is the blue arrow here. When you project it in the space.
Okay, so if you move along that line, then you're gonna gain on the user utilities.
Yes, we will have a higher level of user utility
But
because it's just linear.
at the same time, you have a larger distance to epsilon star.
Yes.
I see.
So obviously this will be a trade-off between the user utility and the item fairness.
Okay.
So so when you touch the borderline, like you touch the the vertex here, you could still like project row to the line here, and you will like continue to follow that projection to some vertex here.
Okay.
So finally, you're gonna get max. You always gonna get endpoint in the Pareto set.
Mm-hmm.
So that's the basic idea of how you try to achieve a Pareto set in the Expohedron. It's quite easy work for you when you explain it in the geometry way instead of algebra way.
Okay. But that's because we have L2 norm, right?
Yes, because we have that, that is what the question I have asked in the future work.
Mm-hmm.
So when you have a point in Expohedron, your next thing you need to do is just like try to decompose it into some property and into property matrix so you can sampling it after. Uh, that's when the character decomposition method with a little bit of chain for the Expohedron come up with.
Mm-hmm.
So you can see the theory of Pareto-optimal in some Google space is not very hard to find. So I will just explain the main idea in the geometry way in here. So the Pareto-optimal said that you could like decompose one point inside an vertex convex here into some almost endpoint, some with uh, uh, some with scale almost endpoint in here, and just simply project it, like draw a line through it. And here the process, this is an example when we have an uh, hexagon here. So we try to create to like decompose the variable x into some of like 3 point, some with scale of 3 point, three vertices here. So we just choose an any kind and first any first point. we draw a line from that point with through it, and it will cut a hyperplane in the lower dimension. In this case, there will be an edge at P2 here, and we will continue to draw a line from some vertex with the same area of this. In this case, V2 cut the from the V2 and to the P2 and cut the final vertex in P3. So by this way, we can decomposition X into some with scale of 3 point here, V1, V2, and V3. The process will like repeatedly until you just like um, reach the final vertex here. So with the scale, because this will be like a probability of the whole of the like the whole permutation, we could just like sampling from the probability, which is the scale of the sum. That should be enough for you to choose a permutation, maybe an order of the recommended list.
I see. So this basically the procedure to go from a point in this
Just
experiment.
go from a point in Expohedron to some kind of like matrix of probability item like this. But instead of like the whole cell point here, they will like decompose to like uh, uh 0.2% of to be this order, 0.2% being this order, and maybe the last will be 0.6% and
Mhm.
0.6 to be this order. So they just like to need sampling for that.
Okay, I see.
Yes, some because since this will have the only the complexity of like uh, n log n,
Mhm.
and this will be n log n too because we have sorting here. So the whole complexity of two set will be n log n. It's very small compared to the like to the n n half n half 5 here, and you will see the very impressive result in the experimental result. Instead, in a two data set, real world data set here, MS, LR, and track here, with the quadric programming, as I said in the proposed in the related work here, they consider it as true Pareto front objective, true Pareto front. You can see that they proposed method with exposure generate a quite exact Pareto fund with the quadric programming here. But the complexity time is small, very small compared to this. So I think this is a very interesting way to find a Pareto workfront. Instead of you just try to using the algebra algorithm to solve the problem, you could like think in the geometry way. So again, that's the whole idea of the paper introduction to Expohedron in the uh, using Pareto front. Um, so what should we do next with Expohedron? First, because in here we have a assumption that the the vertex here will be an uh, position by exposure. Could we change the definition? Yes, they have the follow up paper is dynamic Bayesian Expohedron. Uh, here, In this paper, the main idea is still based on the optimized pathway will still based on the Expohedron, but since the definition of the vertex chain in here, we will have some like an uh, they will imply an idea that when the recommended list is way too long, they will the user will just like pass over, just ignore the rest of the recommended list. It's just like they're gonna consider it. They will try only to see about 10 or maybe 20 first item in the list. Although you see that they will have some exposure score, but the user just like simply don't care about that. They will just ignore that. So they will don't gain any exposure at all.
Mm-hmm.
In the time the vertex will like a little bit change because they will not be like an pentagon with a central like this. It's gonna be like a little bit like not really asymmetric in here. As you can see, that it's not really asymmetric anymore.
Okay, so
So
what has changed? Like they
the
only
chain is a projection on the lower space because sin is not like completely asymmetric. They will say that the uh sorry here. This is the minimum. They will define like a normalized unfairness here. And because since the it's not completely like asymmetric uh, with the central is the equal exposure, so the optimal point will be a little bit changed because it's not asymmetric anymore. So they will have to change the projection on the lower space, but the main idea is still the same. They just only change the projection.
mm,
Like
I
when
thought
they project.
I thought they changed the way of measuring the exposure. Uh,
Yes, because they change the way of measuring the exposure when in the list, it make the expohedron like now not asymmetric anymore. So the optimal point is not like the completely the is the like the intersection point between your own projection. In
okay.
here in here you just simply like project directly
Mm-hmm.
into the lower space and you will gain an optimal point to
Mm-hmm.
follow up that direction. But in here, because it's not asymmetric anymore, so you cannot like directly position here. You have to change it a little bit to find an optimal point.
Okay.
But the
Okay.
same idea stay the same. They only change the projection because the vertex change the definition.
Okay. I see.
That's another way. That's another idea about how they like use Expohedron in the recommended system with a different definition of vertex and a little bit of twist in the projection.
Okay. But so the whole idea is still
Yes, still idea is still the same. They still like following the role, the transport role here, and still project it in the faces, and still try to like make the intersection of the line and there's a circle here is optimal point in the Pareto. Still the same idea.
okay.
So that what the original author have follow up with their original paper. And again, my own thought of this paper. First, if the unfairness is not L2 norm as you said before, could we find the Pareto set? It will be another hard question because as you can see that maybe in this example I use L1 norm, we cannot like differentiate in the solution, and you will see that the intersection point will not be optimal point anymore.
Mm-hmm.
We could not like start from the central and follow up the transpose row, because right now the intersection point is not like the optimal point. The follow-up direction is not the best one anymore, because if you follow that direction you will see that the cutting point here, but if you follow this direction you will see that yes, the the utility will still raise up, but not like sharply like when you follow in this,
Mm-hmm.
but you will have a higher chance to like reach a pickup point here.
I see.
So that's the first question, that if we don't use like L2 norm or maybe some non-differentiate uh, distributions uh, uh, method, could we still use this? Is my first question. And secondly, that's because sin is just an item item finish, but most of the provider not like provides one item. They usually provide more than one item. So if we still want to achieve that provider fairness now, this means that we will like have to group the item from one provider and try to like fair their exposure. So in this case, could we still use a Expohedron here? Uh, because as you can see, the usability might not change, but the fairness will change. The fairness unfairness measurement will change. So this means that the first, because we like the multiplies with a matrix lead to the lower space. So that means that we will have more than one central. It means that we will have some more than one epsilon to generate like epsilon star.
Mm-hmm.
So we will have more than one central. And secondly, because it still be a projection like in the lower space, our level of unfairness will not be like a circle in here anymore. So it's very hard for you to find like a tangent or maybe a projection on level here. Because it's still on convex, it might be some like hyperloid in the higher dimension, but we still need to handle first is the tangent, is the intersection point, could be the maximi point, and secondly is where should we start when we have many epsilon here.
Mm-hmm.
And let me draw something like, for example, in like this, instead of we having just like an
No, no, I understand. I understand your point. I'm just thinking like, uh, do we really need to so far what they actually search is only the intersection of the direction that gain the most for the utilities, but at the same time like the geometry has changed, the shape uh, of the level curve has changed. So we can we actually think about an update procedure or a search procedure in which it I mean I think that there are a lot of optimization technique in the domain of multi-objective optimization where they actually try to balance between the update direction of the two functions, right? You have to balance between those two. So
Yes,
can
it's like the multi-gradient one, right?
yeah, something like that. So
Yes, I have thought about that idea. So, and I'm still wondering because if I follow the multi-gradient, the line I draw in the Expohedron,
mhm.
if that would be the optimal Pareto front, or maybe like a very approximate one.
So that lead us to an approximate solution. But if we can prove that that approximation can be um, habitually good uh, by adjusting some parameters, then we probably can do something interesting there. Like because of the geometry has changed, so it's not simple as in the case of, let's say, autonorm and the symmetric expohedron anymore. But what happened if we use some multi-gradient method and then we obtain some sort of approximate solution, and we can actually prove that by adjusting something, we should be able to obtain a good enough approximation solutions. So I mean, it is a question to think about, and of course, it should be a challenging question, but we cannot rely entirely on the a geometric explanation or geometry solution for this, right? When the geometry is not good for that approach.
Yes, that's the first idea, and the second thing I'm thinking of is just like, could we like change the projection like in the paper, because then since the intersection is not like the optimal anymore, they will change the intersection formula a little bit. So
Yeah.
could we change it to adopt with the with the group group item fairness or not? So that is another question to me.
Yeah. So that like we it's basically like how do we define um good such procedures, and it could lead to a good solution, but it could lead to a bad solution. So when we define a new procedure, we should be able to prove that it should converge to a good enough solution. But the thing is that we also need to prove that it will converge to some solution.
Yes, because they just still a convex thing, so like basically they still gonna be like mm, convert, but like could we prove that maybe fast enough or maybe good enough? It's just like mm, those are a global optimal one, or maybe just like local ones. That's we need to prove.
Yeah. Okay.
Yeah, so that is the end of my presentation.
Okay. Thank you, Phương. Any question from Long and Vũ?
No, I don't have any questions.
I don't have any question.
Okay. Do you understand everything? Okay. So I think it's an interesting paper, and so the reason is probably the function that they use is also support this sort of geometry based approach. But
Yes, it's like they train
when,
from the algebra one to the geometry one. It's just like a completely different way to think about define optimal Pareto-optimal. It's not a
Mhm.
black box anymore. It's just like you can see it in your pathway.
Yeah, but when we change the function, then the geometry will be more complicated.
Yes.
In that case, we have to be more creative in the sense that we cannot rely entirely on the geometric solutions.
Yes,
Geometric,
it's like it's gonna be adapt every time like we change some definition in that.
right? Okay. Okay, good. So interesting, and we should have some development on this